16 and 17 are both looking at asymptotes. The first ones are vertical that we look at for number 16. Now remember, when we're looking at vertical asymptotes, the idea is that we want to look at fully simplified rational functions. And the reason we look at fully simplified is because even though we're focusing our energy on the denominator here, on looking at what will make this equal to 0, we still know that if something off the bottom cancels with the top, whatever that number was that would have made it 0 would be a whole. So there's two options when something on the bottom makes it a 0. It could be a whole, or it could be a vertical asymptote. If it's a whole in the picture, that means it canceled off. So wholes cancel, and the vertical asymptote is just there. It's like the forbidden asymptote, the forbidden region, versus just a forbidden whole. Okay. So in other words, the first thing that we want to do here is to try to simplify our rational equation here, our rational function. So I'm going to factor these, and I'm going to come to the top of the paper here. Again, I use grouping method like it's going out of style, so I'll continue to use that to be consistent. Let's see, I have multiply to be -6, add to be 6. That would be, can we do that? Let's see. Because the multiples of 6 would be a 1, 6, 2, or 3. I don't think we could do that. Very interesting. Okay. So since we can't simplify the top, we don't even need to waste our time trying to simplify the bottom. Because what that tells us is this whole thing will not be an option. If this right here cannot be simplified on top, if it can't be factored, then the denominator, there's no purpose. There's nothing that's going to cancel for sure. So let's just look at the denominator then and see what makes it equal to 0, since we're not allowed to have 0 in our denominator. So I'm going to say we can't factor at the top up there. But as far as the denominator goes, we're still interested in what would make it 0 because that's not allowed. So now we're clearly solving just for vertical asymptotes. So now I'm going to try to factor the bottom. Let's see, multiply to be -35, add to be 2. That sounds like a 7 and a 5, where the 7's positive and the 5's negative. So I'm going to split my middle term using those numbers. So I have x squared minus 5x plus 7x minus 35 equals 0. I'll pull off my x minus 5. You guys can use whatever method it is you use. Now, in other words, you can use trial and error if you want. Right here, I'm personally going to choose to pull off a -7. Wait, no, I'll keep it a +7. And what I'm looking at is I want my x to match the first one that I have times. So I know I want 7 times a positive x, and then hopefully times a -5, which is going to work. 7 times a -5 gives me that 35 back. So on the bottom I'm getting x plus 7, x minus 5 equals 0. In other words, I'm not allowed to have x plus 7 cannot be equal to 0, and x minus 5 cannot be equal to 0. So I have two vertical asymptotes. Since x cannot be equal to -7 is what that means, and x cannot be equal to +5, my vertical asymptotes, those forbidden regions, happen at the exact lines that I'm not allowed to have. So the line x equals 7 and the line x equals 5 are my two vertical asymptotes. So remember, the vertical asymptotes are really easy. It's basically what we used to do when we were looking for domain. What on the bottom makes it equal to 0, because that is forbidden. The only thing that can come up is it canceling or is it just staying there? In this example, since the top couldn't factor, it stayed there, meaning you have a whole dotted line, if you were to draw this, where your function cannot reach. Number 17 is the more fun type. Horizontal asymptotes. We have a little bit more crazy things to recall that will help us in solving this. Include that when we're looking at the powers, of course we still list it with the highest power of x down on top and bottom. And when you're looking at the powers, or the degrees on those x's, the idea is that if your numerator, the stuff on top, is smaller than the power on your denominator, then your asymptote will be y equals 0. That's option number 1. Option number 2 is if they are equal. So if the power on top, that degree on the x, the highest one, is the same as the one on the bottom, then what you actually do is you take the coefficients of top and bottom, so like the 7 and the 4, for example, the numbers in front, and you just put one on top of the other, the top being on top, the bottom being on bottom. And that's your that's your horizontal asymptote. The third option here that we've discussed is that if the top, the numerator power up there, is bigger than the denominator. In this case, you have no horizontal asymptote. But the idea is that sometimes it's possible to look into the slant if there's exactly a difference of 1. So if the top is exactly 1 more than the bottom, can look at slant asymptote. And that wasn't really much of a focus in this class. It's just something for future notes, that it is possible to have an actual line other than just a y equals or an x equals when you're talking about vertical. A slant one would be a line that kind of cuts through the picture. Okay, so looking at this one, it's actually a pretty nice one, because notice our powers are the same, the highest powers. So we are in this one. We're in number 2. So all we do is we just take these two numbers, 7 over 4. So we say, okay, yes, we have a horizontal asymptote, and it is y equals the 7 over the 4. And again, that's only when the top and bottom powers match. Otherwise, you're in one of these other cases. So my horizontal asymptote is 7/4. Okay, use graphical methods to find any turning points of the graph of the function. So this is encouraging us to use technology right away for number 18. And we could actually, I'm very tempted here to factor that and take a look at it. But we'll actually graph it first and just see what happens. Okay, so be careful with your parentheses when you put this into your calculator. Remember, some of you guys can hit, I think it's second F1 or something like that to get a nice fraction. But the rest of us need to be certain that we clear points on this picture. All I need to do is be able to identify this. And then what I'm going to do is say second calc. I'll use minimum on the right to see if that'll give me a value. Oops, on the left. There we go. On the right, then guess. So one turning point is going to be at x equals 6.38 approximately. Y equals 8.28 approximately. The other turning point, so I'm going to say second calc. This time I'll call it a maximum. Approximately there, and we have one at the 0.30 as turning points. Okay. For the given rational function, find all values of x for which y is the indicated value. So in other words, we have here x plus 2 over x minus 1 equals 4. And the idea is that we have to be very careful with multiplying both sides. We're doing cross multiplication. We can do that, but we need to make sure we note things like what we are not allowed to have in the denominator. So the first thing I'm going to say is, you know what, let's just note here that x is not equal to 1. We can't get a 1 on the bottom or it's going to mess up our problem. And then you can do basically whatever you want. I'm actually just going to get common denominator. So I'm going to put x minus 1 here and x minus 1 here, so that now our denominators match. In other words, x plus 2 is equal to 4 times x minus 1. And again, guys, once I've noted the x not equal to 1, I really could have just cross multiplied there. But a lot of textbooks will warn us to be careful when dealing with rationals and cross multiplying. So therefore, just make sure you note that before you cancel it. Okay, so here we have x plus 2 is equal to 4x minus 4. And then we just use regular algebra to solve. So I'll say minus x to both sides, or subtract x to both sides. 2 is equal to 3x minus 4. Adding 4 to both sides. Value there. I'll just say x equals 2. And of course you can look that up on your screen by looking at the picture to verify that you're getting the right answer. Okay, using algebra to solve these two, which are very similar to the one we just did. Here it's safer to cross multiply because notice in the denominator we do not have x's. If we had x's, we could cross multiply as long as we make a note of the fact that you couldn't have whatever invalid x value you had in the bottom, or, you know, invalid possibility you had for the domain. So here I'm just going to cross multiply. And since it's just plain numbers, we're good. 3 times x plus 1 is equal to 2 times x plus 2. So I get 3x plus 3 as I distribute, and 2x plus 4. I'm going to subtract 2x from both sides. So let's see, I'm getting x plus 3 equals 4, minus 3 from both sides. I'm getting x equal to 1. And of course, it's easy to check these. You can put one side into y1, one side into y2, and use crossing graphs if you want. You can also just put the x value in. 1 plus 1 over 2, that's a 1. 1 plus 2 is a 3, over 3 is a 1. So we have a valid